You know, if you stand on the deck of a ship and look out at the ocean, it is incredibly easy to just get completely mesmerized by the surface.
Oh, yeah, definitely. You just see the waves crashing.
Right, exactly. The waves, the whitecaps, the sea spray catching the light. I mean, it's loud, it's highly visible, and it demands your immediate attention.
Yeah, it's practically screaming at you.
But if you actually talk to an oceanographer, they'll tell you that the surface froth is practically irrelevant to the actual mechanics of the Earth.
Right, because all the real power is completely invisible from the surface.
Exactly. It is the deep water currents moving like millions of tons of water silently miles below the hull of your ship. That's what regulates the planet's temperature and the climate.
You know, that is a brilliantly accurate framework for understanding exactly where we are right now with technology.
Yeah,
Yeah, because what we see every day, that surface froth, is super loud and distracting. But the true paradigm shift is happening deep down in those silent currents.
and that is exactly our mission for you on today's deep dive. I mean, if you're listening to this on your commute right now or while you're making dinner, you are probably exhausted by the massive, overwhelming hype cycle surrounding AI.
Oh, completely. The world is just incredibly distracted by the whitecaps right now.
We see, chatbots generating funny pirate poems.
Right, or image generators making pictures of astronauts riding horses on Mars.
Yeah. And look, that stuff is fun. I mean, it's wildly entertaining, but it is not the revolution. The real AI revolution is completely invisible to most of us.
It really is. It's out there right now predicting global weather patterns or designing novel pharmaceutical drugs from scratch.
Yes, discovering entirely new physical materials and solving biological mysteries that have baffled the smartest scientists on Earth for, like, half a century.
So, to map those hidden currents today, we have a phenomenal grounding source for this discussion. We are analyzing a really fascinating, incredibly in-depth conversation between a prominent interviewer and Demis Hassabis.
The CEO of Google DeepMind.
Yes, exactly. Who also happens to be a recent Nobel Prize winner. And the setting for this source interview is uniquely brilliant.
It's so good. They're sitting across from each other, literally playing a game of Jenga.
Right. But in this game, every single wooden block represents a cutting-edge AI project his team has actually built.
So you have blocks for Gemini, for AlphaCode, for Gencast, AlphaFold.
And as they pull these blocks out one by one, they are quite literally deconstructing the architecture of modern scientific discovery.
But before we even get into what those blocks represent, we really have to talk about Hassabis himself. Because I firmly believe you cannot understand the trajectory of this technology without understanding the mind that set it.
No, his background is wild. It reads like a comic book origin story for a super scientist.
It really does. He was a childhood chess prodigy, and by the time he was 17 years old, he was such an exceptionally gifted programmer that he was offered a reportedly million-dollar job in the video game industry.
Which is just, I mean, put yourself in those shoes
Almost any 17-year-old on the planet would take that money and run.
instantly. But he turned it down. He decided to go to college instead, eventually earning a PhD in cognitive neuroscience.
So he was actually studying the physical mechanics of the human brain.
Right. And then he goes on to found DeepMind with what has to be the most audacious, borderline arrogant mission statement in Silicon Valley history:
Oh man, what was it?
to solve intelligence.
Wow. Solve intelligence. That's an ambition that forces you to pause. Like, how do you even begin to operationalize a goal like that?
Well, what is absolutely crucial to understand about his philosophy, and this really sets him apart from many other tech founders, is that he never viewed AI as a product to be sold.
Right, it wasn't about an app or a subscription.
Exactly. For him, AI was always meant to be the ultimate tool, a crowbar to pry open the mysteries of the universe.
He wanted to build an intelligence that could accelerate scientific discovery, cure multigenic diseases, and, like, fundamentally understand the nature of reality itself.
Yeah, and when he eventually sold DeepMind to Google, he did it specifically because they promised to provide the massive computational power required to let his team focus purely on foundational scientific research.
Of course, the landscape has completely fractured and shifted since then. I mean, today, he is essentially in charge of all of Google's AI efforts,
Which means he is making decisions that impact billions of lives every single day.
which is exactly why you, the listener, need to understand what's actually happening here. I want to look past the chatbots. I really want to unpack how AI is stepping out of the browser window and into our physical reality.
Into our biology, our power grids, our medicine.
Right. It is moving from pixels to molecules.
And as we unpack this, our job today is to maintain a really rigorous analytical perspective. perspective. Because when you hear the scale of what these systems can actually do, the human brain defaults to viewing it as magic.
It completely sounds like science fiction.
But it's not magic. It is highly advanced computation. So we have to consistently look at the why and the how of these systems. We need to evaluate them not as mystical oracles, but as unprecedented tools.
Right.
And to understand where this is all going, we first have to answer a deceptively simple question. What does the word intelligence actually mean in the context of a machine?
Okay, yes. Let's start exactly there. Because if we look at the history of computers, we actually have two completely different eras of artificial intelligence. And comparing them clears this up immediately.
You're talking about the expert system era versus the learning system era.
Exactly. For the expert system era, we have to travel back to the 1990s. The defining cultural moment of that era was IBM's supercomputer, Deep Blue, playing chess against the world champion Garry Kasparov.
And beating him.
Right, and beating him. At the time, all the headlines proclaimed that computers had finally outsmarted humanity. But in the source interview, Hassabis points out something critical. He says Deep Blue wasn't actually intelligent at all.
And he's entirely correct. To understand why Deep Blue lacked actual intelligence, you have to look at the mechanics of how it was built. It was a classic expert system.
Break that down for us. What does that mean in practice?
It means a team of brilliant computer scientists sat down in a room with a team of brilliant chess grandmasters. The grandmasters basically explain their human knowledge, their rules, their opening strategies, their heuristics for valuing different pieces on the board.
Right, like a knight is worth this many points in this scenario.
Exactly. The programmers then hard-coded that human knowledge into the machine. Then, they hooked that code up to a massive supercomputer that could brute force search millions of potential outcomes per second using those human-provided rules.
Wait, let me make sure I'm grasping the distinction here. You're saying the machine wasn't really thinking about chess.
No, not at all.
It was just executing human thoughts at superhuman speed. It
Mhm.
was basically just a massive calculator following a script.
That is the exact distinction. The intelligence didn't reside in the silicon of the computer. The intelligence resided entirely in the organic minds of the human programmers and the grandmasters who wrote the script.
Wow.
The computer was just a very fast, very dumb executioner of instructions. And Hassabis offers the perfect, elegant proof for this. He points out that Deep Blue, despite being the undisputed world champion at chess, could not play a game of tic-tac-toe.
Which is such a bizarre concept to wrap your head around. I mean, it can beat Garry Kasparov, but an average 5-year-old child could completely destroy it at tic-tac-toe.
Yep, because the machine literally wouldn't know what the X's and O's were.
Because nobody programmed those specific rules into it.
Right. It couldn't generalize its knowledge even 1 millimeter outside of its rigid, pre-programmed lane.
And that's the key, isn't it? Generalization.
Precisely. Generalization is a hallmark of true intelligence. If you learn the underlying logic of a complex game, you should definitely be able to adapt to a strictly simpler game. But Deep Blue couldn't.
So it was a dead end.
Basically. So, to move past this dead end, the DeepMind team knew they needed a new architecture, a learning system. And to test whether a machine could actually learn, rather than just execute rules, they needed a proving ground that was mathematically impossible to brute force.
They needed the ancient game of Go.
Exactly.
Right, Go. The oldest board game in continuous human history. For anyone unfamiliar, it's played on a grid with black and white stones. And when we say it can't be brute forced, we need to put some real numbers on that for the listener.
Oh, the numbers are staggering.
Chess is complicated, absolutely.
Yeah.
But Go is on another plane of existence entirely. The number of possible board positions in a game of Go is 10 to the power of 170.
Which is just a fundamentally incomprehensible number.
Totally. To put that in perspective, there are only about 10 to the power of 80 atoms in the entire observable universe.
Wow.
Yeah. If you tried to build a supercomputer to brute force check every possible Go move like Deep Blue did with chess, the universe would literally experience heat death before the computer finished its calculation.
Right, so brute force is literally physically impossible.
Because the math is so overwhelmingly vast, human Go masters don't play it like an equation. They play it based on aesthetics. They talk about moves feeling right or looking beautiful. So my question is, how on earth do you program a machine to have a feeling?
Well, you can't. And that was DeepMind's brilliant realization. You cannot program intuition. So instead of trying to hard code the rules of good Go, they built a system called AlphaGo using an architecture called deep reinforcement learning.
Okay, how did that start?
Initially, they fed AlphaGo a massive database of human games from the internet. The AI studied these games just to learn the general patterns of how humans tend to play.
Okay, so it starts by mimicking us.
Right. But then, and this is the critical innovation, they combined that pattern recognition with a mechanism called Monte Carlo tree search.
Okay, stop right there. Monte Carlo tree search is exactly the kind of jargon that makes people tune out.
Fair enough.
Explain that mechanism to me. How does that actually work in practice?
Let's use a physical analogy. Imagine you are standing at the edge of a massive, impossibly dense forest. The forest represents all the possible moves in a game of Go. Your goal is to find a path to the other side, a victory.
Okay, I'm with you.
Now, you could try to walk down every single branching path one by one to see where it leads, but as we established, there are more paths than atoms in the universe. You would die trying. That's brute force.
Right. So what's the alternative?
Imagine you have 1,000 scouts. You send them running into the forest completely at random. Most of them get lost or hit a dead end, but a few of them eventually stumble out the other side.
Oh, okay.
You look at the general direction those successful scouts took and you say, okay, that general area seems mathematically promising. So next time you send 1,000 scouts, but you bias their starting direction toward that promising area.
So you're narrowing it down.
Exactly. You are using random sampling, the Monte Carlo part, named after the casino, to estimate the probability of success down different branches of the decision tree without having to map the whole tree.
So it's not checking every move. It's essentially developing a probabilistic intuition about which areas of the board are worth exploring deeper.
Yes.
Which perfectly sets the stage for one of the most famous moments in computer science history.
Yeah.
March 10th, 2016. AlphaGo is playing a highly publicized multi-game match against Lee Sedol in South Korea.
And Lee Sedol is basically the Roger Federer of Go, a legendary, dominant world champion.
Over 200 million people are watching this match live. It's game 2 of the series. And then the machine plays move 37.
Move 37 is legendary for a reason. AlphaGo placed a black stone on the 5th line of the board, relatively early in the game. To anyone who knows Go, this is deeply shocking.
Why?
It is a move that completely defies thousands of years of established human conventional wisdom. Hassabis notes in the interview that if a human student played that move, a Go master would literally slack their wrist. It's considered objectively bad, inefficient, and bizarre.
Yeah, if you watch the archival footage of Lee Sedol when it happens, you actually see his physical reaction. He stares at the board, he gets up, and actually has to leave the room for a minute to compose himself. He's completely baffled.
Even the commentators thought it was a bug.
Exactly. The expert commentators on the broadcast assumed the machine just suffered a glitch and made a terrible mistake. But then, as the game unfolds, 100 moves later, the board state gets incredibly complicated. A massive battle breaks out across the entire grid.
And guess what happens?
That one seemingly random, bizarre stone on the 5th line ends up being in the exact mathematically perfect position to save AlphaGo's position and win the game. It wasn't a glitch at all. It was prescient.
And this is exactly why Move 37 is widely considered the dawn of the modern AI era.
Why is that the specific turning point?
Because it proved, irrefutably, that a machine could generate a genuinely original idea. It wasn't just regurgitating human data. It wasn't executing a human script.
It was doing something new.
Right.
Yeah.
It had used its Monte Carlo scouts and its deep learning to explore the mathematics of the game. And it synthesized a creative strategy that no human being had ever conceived of in the thousands of years the game has been played.
Okay, but isn't calling it creativity giving the machine a little too much credit?
Yeah.
I really struggle with the philosophical weight of that word here. It's just a statistical parlor trick, right?
How do you mean?
Think about it this way. If an alien lands on Earth, and this alien's eyes process entirely different light spectrums than ours do, it sees in ultraviolet and infrared. And it paints a painting based on what it sees. Is the alien being creative? Or is it just working with a different set of mathematical inputs that our human brains simply lack the hardware to perceive?
You know, that is a fascinating tension to highlight, and honestly, the AI community wrestles with this constantly. The machine isn't experiencing the emotional rush of creativity, no. It doesn't feel a spark of inspiration. Your alien analogy is highly accurate. AlphaGo explored a mathematical probability space that was previously invisible to the human eye, much like an alien seeing ultraviolet light. It found an objective truth on that board that we couldn't see.
So it's just math we couldn't access.
Exactly. But whether you call it creativity or statistical probability, the output is the same: novel, highly effective solutions that humans could not generate on their own.
Okay, but for the listener who doesn't play Go, I have to ask the practical question. Why does a board game matter? I mean, it's a neat trick, but it's just wooden stones on a grid.
Yeah.
How does an alien seeing ultraviolet light on a Go board affect my real life?
Because a board game is just a sandbox, the DeepMind strategy was never just to win games.
What was it then?
Games are the perfect proving ground because they have constrained rules and a clear win-loss state.
Yeah.
You can measure progress perfectly. But once AlphaGo proved that this specific neural network architecture could discover genuinely original solutions in a constrained environment.
You took it out of the sandbox.
Exactly. They ripped it out of the sandbox and pointed it directly at the biggest unsolved mysteries in the real world, starting with human biology.
Which means we are moving from moving stones on a board to moving the very building blocks of life. The DeepMind team decided to take on what is essentially the biological equivalent of Fermat's last theorem, the protein folding problem.
To understand the magnitude of what they accomplished here, we need a brief primer on how biology actually works.
Go for it.
Proteins are the fundamental workhorses of all living things. Everything your body does, digesting your breakfast, fighting off a cold, firing the neurons that allow you to hear this sentence right now, is executed by proteins.
Right, they do everything.
And the function of any given protein is entirely dictated by its specific three-dimensional shape.
But here's the catch, right? A protein doesn't start its life as a 3D shape. When your DNA gives the instruction to make a protein, it starts as a one-dimensional string of amino acids, just a long, flat line of biological code.
A 1D string.
But then, within milliseconds in your body, that 1D string crumbles and folds in on itself, contorting into an incredibly complex, tangled 3D structure. And the rules of how it folds are governed by complex atomic forces. Some amino acids repel water, some attract it, some bond to each other.
It's incredibly chaotic.
Exactly. For 50 years, the absolute holy grail of biology, known as Anfinson's dogma, was this. If we know the 1D sequence of amino acids, can we computationally predict the final 3D shape? And for half a century, it was considered virtually impossible.
Because the math is just as complex as a game of Go. A single protein can fold into astronomical numbers of possible configurations.
So how did scientists do it before AI?
Before AI, the only way to figure out a protein shape was through excruciating experimental trial and error. You had to physically isolate the protein in a wet lab, then you had to crystallize it.
Which is hard, right?
It's extremely. Organic proteins generally do not want to form neat crystals. If you successfully crystallized it, you would shoot powerful X-rays at it, study the diffraction patterns, map the electron density, and slowly piece together its atomic structure.
Wow.
This process of X-ray crystallography could take a PhD student 5 years of their life and cost hundreds of thousands of dollars to map just one single protein.
It sounds maddening. I mean, here's my analogy for how frustrating that old physical method is. Imagine I give you a completely flat piece of paper, and it has all these faint overlapping crease lines on it.
Okay.
And I tell you, this is an origami swan. But you are absolutely not allowed to solve it. You just have to stare at the crease lines on this flat paper, do some complicated math, and draw me a perfect 3D rendering of what the swan looks like.
That's a brilliant comparison. It's an insane request.
Right. But then, enter AlphaFold. DeepMind applied the same learning philosophy that conquered GoToGo to the biological data of proteins. If Go was a game of placing stones, protein folding was a game of placing amino acids. AlphaFold became a magical scanner that looks at the flat paper and instantly renders a perfect 3D model of the origami swan. And this leads to a moment in the source interview that I think perfectly encapsulates the dizzying speed of AI right now. It takes place in a routine DeepMind meeting in 2021.
Oh, yes. That meeting is a perfect illustration of a paradigm shift. Originally, the DeepMind team's plan for AlphaFold was quite modest, relatively speaking.
What were they going to do?
They were going to set up a server, essentially a web portal. Scientists from around the world could email DeepMind a specific 1D protein sequence they were struggling with. The AlphaFold system would process it over a few days and then email them back the predicted 3D structure.
Right, like a software as a service thing.
Exactly. That was the standard, accepted way computational biology services worked.
But then, during this meeting, Hassabis is just sitting there fiddling on his phone. He's doing a quick back-of-the-envelope calculation. He realizes that AlphaFold is not only astonishingly accurate, it's incredibly fast.
Right, it was doing them in seconds.
Yeah. He thinks, okay, there are about 200 million distinct proteins known to science across all of nature, every plant, every animal, every bacteria, and since AlphaFold can fold one protein in about 10 seconds, he does the math on his phone and realizes
If they just buy more server space and scale up their compute, they don't need to wait for scientists to email them requests.
they could just fold every single protein known to humanity in one single year.
So they changed the plan immediately. They preemptively solved the 3D structure for almost every biological entity on Earth.
And then, crucially, they release that entire massive database for free to the global scientific community.
The scale of this achievement cannot be overstated. Today, over 3 million scientists, which is essentially every working biologist on the planet, use the AlphaFold database. It has completely bypassed decades, perhaps centuries, of physical, grueling lab work.
The Source interview highlights some specific, real-world applications of this that just blow my mind. Let's look at neglected diseases. There are diseases like malaria, Chagas disease, and leishmaniasis that devastate hundreds of millions of people, primarily in developing nations.
Right, terrible diseases.
But because there isn't a massive, lucrative profit motive for big pharmaceutical companies to prioritize these, the research is largely left to nonprofits and university labs who are chronically underfunded. They simply do not have the money to spend 5 years and $1 million crystallizing a single malaria protein.
Exactly.
But now, AlphaFold just gives them the structure for free. They get to skip the hardest, most expensive part of the structural biology entirely and jump straight into trying to find a drug to cure it.
It is a massive democratization of scientific research, and it extends far beyond human medicine. The source material mentions botanists researching resilient crops to combat climate change.
Like wheat, right?
Yes. Take wheat, for example. Wheat has a bizarrely massive and complex genome. It has multiple overlapping copies of its genetic material, making its proteins incredibly difficult to study structurally.
Right, because it's just so dense.
But with AlphaFold, plant scientists can instantly access the 3D structures of wheat proteins, allowing them to rapidly engineer crops that can survive harsher droughts or resist emerging pests.
My absolute favorite example from the source is the nuclear pore complex. This sounds like a structure from a sci-fi megacity. It's one of the largest proteins in the human body.
Yeah, the gateway.
Exactly. It acts as the gateway, like a massive biological donut ring that opens and closes to let nutrients and instructions in and out of the nucleus of your cells. For years, scientists couldn't see its structure clearly because it's just too massive and complex to crystallize.
Too many moving parts.
Right. But AlphaFold, working alongside fragmented physical experimental data, finally helped decode this beautiful, intricate gateway. We can now literally see the doors to our own DNA.
It's amazing. But this incredible biological breakthrough introduces an entirely new bottleneck.
Which is?
Having a perfect map of a locked door is wonderful. But a map doesn't open the door. You still need to forge key. Knowing the shape of a disease-causing protein doesn't automatically cure the disease. You have to invent a chemical compound that interacts with it.
Ah, right.
And that reality shifts us from simply mapping biology to actively engineering medicine.
Which leads us to a DeepMind spin-off company called Isomorphic Labs. If AlphaFold found the locks, Isomorphic is trying to forge the keys. Because let's be completely honest, the current drug discovery process is fundamentally broken.
Oh, it's a nightmare.
Right now, on average, it takes about 10 years and billions of dollars to bring a single new drug to market. And the most agonizing part, there is a 90% failure rate. 9 out of 10 drugs that look promising in the early stages end up failing in late-stage clinical trials. It is agonizingly slow, incredibly expensive, and deeply inefficient.
And the reason for that staggering failure rate is biology's inherent complexity. If you want to stop a disease, you might need to block a specific protein from functioning. So you design a chemical compound, a drug, that fits perfectly into a specific pocket on that target protein's 3D surface, like a key in a lock.
Seems simple enough in theory.
That's hard enough on its own. But the human body has roughly 20,000 different types of proteins floating around inside it at any given moment.
So it's a crowded environment.
Very. Your newly designed drug might bind perfectly to the target protein, but because many proteins share similar surface shapes, your drug might accidentally bind to a completely different protein in your heart or your liver.
Oh, wow.
That off-target binding is what causes severe toxicity and terrible side effects. That's exactly why drugs fail in phase 3 clinical trials after billions have been spent.
This is where Isomorphic Labs is completely changing the paradigm. They are moving the early phases of this process in silico.
Which means inside a computer.
All right, for the listener, in silico basically means inside a computer simulation, rather than in the wet lab with physical petri dishes, test tubes, and mice. Once AlphaFold provides the 3D shape of the target protein, the AI generates a novel chemical compound to bind to it.
Which is great.
But here's the absolute superpower. Because they have the entire AlphaFold database of all 20,000 human proteins, the AI can take that newly invented compound and virtually test it against every single other protein in your body in a matter of minutes.
It creates an incredibly fast, highly efficient self-correcting loop. The AI proposes a chemical compound, checks it against the 20,000 off-target proteins, notices a slight chemical affinity for a liver protein.
So it flags a potential side effect.
Right, it flags it, tweaks the molecular structure of the drug slightly to eliminate that specific interaction, checks all 20,000 again, and repeats this evolutionary cycle thousands of times in a single afternoon.
That is just wild.
You are doing the grueling trial and error toxicity testing in the simulation, vastly reducing the risks before you ever synthesize the physical drug in a lab. You only take the final, highly optimized candidates into the wet lab for physical validation.
It's like stress testing a bridge design in a computer simulation against hurricanes and earthquakes a million times before you ever pour a single ounce of concrete.
Exactly.
But drug design is only half the battle, right? We also have to know where the disease is starting in the biological code. In the source material, there is an amazing moment where the interviewer brings in a question from another Nobel laureate, Jennifer Doudna.
The pioneer of CRISPR.
Yes, the revolutionary gene editing technology.
Doudna's question cuts to the absolute core of modern genetics. CRISPR allows scientists to act like molecular scissors, literally cutting and editing DNA.
Which is incredible on its own.
It is, but she points out a massive, glaring blind spot in our knowledge. We often don't know what we should be editing. Only about 2% of human DNA actually codes for the proteins we just talked about.
What about the rest?
The other 98% is this vast, dark matter of the genome. It regulates, it turns genes on and off, and it controls complex cascades in ways we barely understand. Her question to Hassabis is essentially, how do we find the exact typographical error in that massive sea of DNA that is causing a genetic disease?
And his answer is a project called AlphaGenome. This is an AI model specifically designed to read those massive billions of letters long genetic sequences and predict whether flipping a single letter, just one tiny mutation, will be completely harmless or if it will trigger a catastrophic multigenic disease cascade.
So it maps the dark matter.
Exactly. AlphaGenome acts as the ultimate proofreader for human DNA.
The potential synergy here is profound. Imagine the Pipeline AlphaGenome scans a patient's DNA and precisely identifies the exact combination of mutations buried in the dark genome that are causing a complex disease. AlphaFold then maps the shape of the malformed proteins those mutations produce. Isomorphic Labs designs a highly specific chemical to temporarily mitigate it, and finally, tools like Doudna's CRISPR are deployed as guided scalpels to go into the DNA and fix the exact root error.
We are talking about a systemic, end-to-end computational pipeline for curing human disease.
It really is?
Okay, here's where my brain starts running away with us, and I need to push back on this utopian timeline. If we are building systems that can simulate the human body's chemical reactions so perfectly in silico, how close are we to a world where a doctor prescribes a drug that literally did not exist an hour ago?
That's a bold vision.
Like an AI analyzes my exact personal genome, simulates a drug uniquely tailored to my specific biology with zero side effects, synthesizes it on the spot in a machine at the pharmacy, and I take it. Is that actually where we're heading, or is that just pure science fiction?
Well, the underlying logic of the technology absolutely points in that direction. Personalized medicine at the molecular level is the ultimate theoretical goal of combining AlphaGenome, AlphaFold, and Isomorphic's chemical design. However, prescribing a drug invented an hour ago is highly improbable in the near term because biology in the real physical world is incredibly messy, and regulatory bodies require physical proof of safety.
Yeah, the FDA isn't going to let an AI print a drug and hand it to you in an hour.
Exactly. And this brings up a crucial tension in the narrative. This utopian vision of methodical, rigorous, careful scientific progress where we take decades to carefully validate medical AI in the lab before public release was exactly how Hassabis originally wanted to proceed.
But the real world and the realities of human capitalism had other plans.
Right. Unpredictable technological breakthroughs and fierce rival companies forced a massive permanent deviation from that quiet, controlled path.
Yeah, we have to talk about the unintended AI race. In the source material, Hassabis gives a remarkably candid quote. He says, if I'd had my way, I would have left AI in the lab for longer.
That's quite a statement.
Think about the weight of what he's saying there. His ideal world was a slow, deliberate, peer-reviewed march toward artificial general intelligence over 10 to 20 years. He wanted to focus purely on narrow, specialized models like AlphaFold to cure cancer and solve scientific mysteries quietly in the background, fully mapping every single step of the technology before moving forward.
It is the classic scientist's dream. Controlled, incremental, safe progress. But that plan was completely shattered by an unexpected reality in computer science.
What happened?
For decades, the entire AI industry assumed that teaching a machine to understand and generate human language would be an incredibly steep hurdle. Human language is full of nuance, sarcasm, and shifting context. They thought cracking language would require several more major, unforeseen conceptual breakthroughs.
Because older models processed language sequentially, right? Like reading a book word by word. By the time the old models got to the end of a long paragraph, they literally forgot what the first sentence was about. They lost the context.
Exactly, they had no memory.
But then, it turned out, language was surprisingly easy to crack thanks to the invention of the transformer architecture, which, ironically enough, was invented by researchers at Google.
The transformer architecture changed everything. Instead of reading word by word sequentially, transformers use a mechanism called self-attention.
How does that work?
This allows the neural network to look at an entire massive chunk of text all at once, analyzing how every single word relates to every other word in that text simultaneously. It processes parallel context.
So it sees the whole picture at once.
Right. Combine the transformer with reinforcement learning, and suddenly, large language models became exponentially, shockingly better almost overnight.
And this leads directly to the ChatGPT effect. Rival tech labs took these massive language models and decided to release them directly to the public as research experiments.
And we all lived through what happened next. They went wildly viral. The public adoption was historically unprecedented, hitting 100 million users faster than any product in human history.
It was crazy.
This sudden, massive mainstream explosion threw the entire AI industry out of the quiet research lab and into a ferocious commercial sprint. And we need to be clear and entirely impartial about what the source material presents regarding this race, because it involves heavy corporate and geopolitical realities.
Right. If we look neutrally at the dynamics described in the source, this race is compounded by two massive factors. First, you have intense commercial pressure. If one Silicon Valley company doesn't release their cutting-edge model, a rival company will, capturing the market share. It's a classic prisoner's dilemma.
Yep, the pressure to launch is immense.
And second, the source notes that this is occurring against a backdrop of macro-level U.S.-China geopolitical competition over technological supremacy. Billions of dollars in capital expenditure are being poured into massive supercomputing data centers, turning this into an arms race of sheer computational scale.
The stakes are incredibly high, and the expert in the source weighs the pros and cons of this frantic new reality quite clearly. Let's examine the cons first.
Okay, what are the downsides?
The primary casualty is the loss of that slow, philosophical contemplation Hassabis martyred. We are now deploying massive models to the public that hallucinate facts, that confidently invent information, and that contain fundamental architectural flaws we don't fully understand yet. We lost the controlled scientific environment.
But the source also outlines the massive pros of this rapid public deployment, and they are significant. First, the speed of progress is lightning fast. The sheer amount of global capital and engineering focus poured into AI right now is accelerating development by decades.
That's true. The funding is unprecedented.
Second is democratization. The general public, you and I, are getting our hands on tools that are only 3 to 6 months behind what exists in the most advanced, multi-billion-dollar frontier labs. That is historically unprecedented. Usually military or corporate labs hoard transformative tech for decades.
And the third pro he mentions is the concept of massive stress testing. You can test an AI in a pristine lab with 100 brilliant engineers for years, but you will never, ever find all the hidden flaws, the strange biases, or the weird edge cases until you unleash it on 100 million unpredictable, chaotic human beings online.
Right. The internet is crazy.
The global public is currently acting as the largest, most aggressive quality assurance team in human history.
So what does this all mean for us? I mean, I really wrestle with this. Is it actually better that we get to play with these slightly flawed, occasionally hallucinating chatbots right now?
Yeah.
Are we basically getting used to the shocks slowly?
Like building an immunity.
Yeah, building up a societal tolerance. Because the alternative is waking up 15 years from now to an omnipotent, flawless AGI system deployed from a secret lab that we have absolutely no context for. Is the messiness actually a feature, not a bug, for human adaptation?
That is a very profound and pragmatic way to frame it. Incremental exposure, even with highly flawed systems, allows society to build cultural, legal, and psychological familiarity with the technology.
So we aren't totally blindsided later.
Exactly. It allows governments to start thinking about regulation before the ultimate system arrives. But here's the catch: to survive this fast-paced, highly competitive race, the AI developers can't rely on slow human inputs or curated human data anymore. They're running out of high-quality internet text to train on.
So they need new data.
Right. The models must become radically more efficient, and they must learn entirely on their own to keep up with the pace. And this necessity brings us right back to the evolution of the games that started it all.
Remember AlphaGo, the AI that beat the human champion with Move 37? Well, AlphaGo had a major fundamental limitation. It was initially trained on millions of games played by humans. It learned our human biases, our blind spots, and our bad habits first before it started exploring on its own.
Yeah, it was tethered to us.
To reach the next level of intelligence, DeepMind realized they had to remove human knowledge entirely. They created the next iteration called AlphaZero. The zero stands for absolutely zero human knowledge. No internet databases, no human heuristics, tabula rasa, a blank slate. They literally just programmed the basic rules of how the pieces move and essentially said, go learn.
The timeline of AlphaZero's learning process is staggering, and it beautifully illustrates the terrifying power of autonomous reinforcement learning.
How fast was it?
AlphaZero learns by playing random games against itself. At first, it's just flailing. It makes completely random, terrible, nonsensical moves. But the system tracks which random flailing accidentally leads to a win and which leads to a loss.
So it's trial and error at light speed.
Exactly. It updates its neural network based on that tiny sliver of success and plays itself again and again. Millions of times. It synthesizes its own data from thin air.
Hassabis describes watching AlphaZero master chess, and the timeline he gives is just haunting. In the morning, you turn it on, and it is playing completely random, idiotic moves. By lunchtime, it has played enough games against itself that it can competitively play against Hassabis himself, who, remember, is a former child prodigy.
In just a few hours.
Yes. By tea time in the afternoon, it is playing at the level of a human grandmaster. And by dinner time on that exact same day, it completely surpasses Stockfish. Now, Stockfish was the reigning world champion chess algorithm that had been painstakingly hand-coded by humans for years.
It blew past years of human engineering.
AlphaZero went from literally knowing nothing, a blank slate, to being the best entity in the universe at chess in a single day. It took just 17 generations of learning against itself.
And this zero approach learning from scratch without human bias is now being applied far beyond board games. Consider a project mentioned in the source called AlphaTensor.
What does that do?
Matrix multiplication is the fundamental mathematical operation that underpins all neural networks. It is the core math that makes AI work. AlphaTensor treated matrix multiplication like a game. It played the math against itself, with the win state being a faster calculation.
And did it win?
Oh, absolutely. And it discovered entirely new, more efficient mathematical algorithms to solve it that humans had never found. It made matrix multiplication up to 5% faster.
Wait, let's just sit with that analogy for a second, because it is mind-bending. It's an Ouroboros, the snake eating its own tail. We have an AI inventing better underlying math to make the AI run faster so it can invent even better math.
That's exactly what it's doing.
That is literally like a car engine learning how to machine its own parts and rebuild itself to be more efficient while you are driving down the highway at 80 miles an hour. And the source mentions another project, AlphaChip, which does the exact same thing, but for physical hardware.
Right, routing the chips.
It figures out how to route the microscopically tiny wires on silicon computer chips better and more efficiently than human engineers can. The AI is designing the physical chips that will power the next generation of AI.
These domains, matrix math, chip design, protein folding, are what Hassabis defines as root node problems. Think of human knowledge as a massive branching tree. Most scientific research happens out on the leaves, making small, incremental improvements to an existing drug or an existing material.
Right.
But root node problems are the massive base trunks of the tree. If you solve a root node, you don't just get a leaf, you unlock an entire massive branch of new possibilities. Solving the 3D structure of proteins was a root node that unlocked the entire branch of modern computational drug discovery.
And the source points out that applying this tabula rasa, zero approach, could completely unlock material science. Imagine setting up a computer simulation with the foundational rules of quantum physics and chemistry.
Just feeding it the raw laws of physics.
Exactly. You tell the AI, invent a new material that doesn't exist in human literature that conducts electricity perfectly. We could discover entirely new battery chemistries that hold a charge for a year. Or the holy grail of physics, a room temperature superconductor.
That would change the world.
That one discovery would revolutionize global energy grids, transportation, and computing literally overnight.
The potential upside is staggering. But, as you pointed out with your car engine analogy, an intelligence capable of rebuilding its own math and operating completely autonomously is incredibly powerful.
Yeah, it's a little scary.
And as we shift from the pristine, controlled environment of a game board or a physics simulation into the messy, unpredictable real world, the risks multiply exponentially. We are entering an era where the AI is no longer confined to a screen.
Right, because technology this powerful is inherently dual use. It can be used to heal, and it can be used to harm with equal efficiency. Let's start with the optimistic, macro-level use cases that Hassabis champions for governments. Imagine deploying this level of AI to optimize massive civic systems. We're talking about revolutionizing public health analytics to stop pandemics before they start, creating hyper-personalized AI tutors for every single student on Earth, and managing national energy grids. The source mentions that DeepMind applied their AI to Google's own massive data centers.
Oh, the cooling project.
Yeah. The AI just looked at the data and managed to save 30% on the energy required for cooling simply by optimizing the flow of air and water in ways humans missed. If you apply that 30% efficiency savings to an entire national power grid, the environmental impact is staggering.
But Hassabis is also very clear-eyed about the macro-level worries, and it's highly instructive to note what he doesn't focus heavily on.
Right, he ignores the small stuff.
Yeah, he somewhat dismisses the minor, everyday squabbles over terms of service, minor copyright disputes, or chatbots saying silly things as secondary issues. Instead, he focuses on two massive existential threats. The first is bad actors.
Meaning who?
This refers to nation-states, terrorist organizations, or even highly capable individuals repurposing these benign tools. An AI designed to synthesize a complex molecular cure for a disease uses the exact same underlying logic that could be inverted to synthesize a novel, highly lethal biological weapon.
It's the ultimate double-edged sword. If Isomorphic Labs can ask the AI, design a molecule that binds to this protein to cure cancer, a bad actor could theoretically ask a stolen or open-source version of that model, design a molecule that binds to this protein to shut down the human respiratory system instantly.
Exactly. The machine doesn't have morals.
The machine doesn't know the difference between healing and killing. It just solves the puzzle you give it. And the second threat he mentions is even more sci-fi, but he puts a very short, very real timeline on it. He worries about the AI going rogue. And he's not talking about 50 years from now. He says this is a medium-term threat, roughly 3 to 4 years away as we enter what he calls the agentic era.
The agentic era is a critical concept for listeners to grasp because it changes our relationship with the computer entirely. Right now, most public AI systems are reactive.
Like a search engine.
Yes. You type a prompt into a chatbot, it gives you an answer, and it stops. It goes dormant, waiting for your next prompt. But an agent is an AI system that is highly autonomous.
So it does things on its own.
Right. You give it a high-level goal like, organize a comprehensive marketing campaign for this new product, and the AI agent goes out into the digital world. It breaks that big goal down into subtasks, it sends emails, it buys ad space, it analyzes incoming data, it adjusts its strategy, and it executes multi-step processes completely on its own without waiting for human intervention.
And as these agents get more powerful and we give them access to the physical world like power grids or financial systems, we face the classic alignment problem. How do you give a highly capable, autonomous agent a goal and ensure it doesn't find a bizarre, dangerous loophole to achieve that goal?
That's the million-dollar question.
Right. If you tell a super powerful AI agent to solve cancer at all costs, how do you ensure it doesn't calculate that the most efficient way to eliminate cancer is to simply eliminate all humans, since humans are the biological hosts of cancer? It's an extreme example, obviously, but it highlights the fundamental logic flaw.
It highlights the profound difficulty of the guardrails problem. You have to specify the constraints so perfectly that the system cannot circumvent its safety programming. The source discusses some immediate, practical mitigation efforts happening right now.
It's like SIMTID, right?
Yes, Synthid. This is a digital watermarking tool that invisibly tags AI-generated images, audio, and text at the foundational pixel or token level. It's designed to combat the immediate threat of deepfakes and mass misinformation.
But that doesn't solve the rogue agent problem.
Exactly. Synthid only solves the output problem. It doesn't solve the autonomous logic problem of an agent. Hassabis stresses that building these guardrails is historically unprecedented. It requires urgent, massive international cooperation between rival labs, academia, and government AI safety institutes.
Okay, here's where my brain starts to melt a little bit, and I have to ask the obvious question. If the AI is smart enough to invent a mathematical concept that humans missed for thousands of years in Go, if it's smart enough to fold 200 million proteins in a year, if it's literally rewriting its own matrix multiplication code to be faster, how on earth can a human programmer ever be smart enough to write a guardrail that the AI can't outthink?
It's a terrifying paradox.
If it's vastly smarter than us, won't it just see our safety constraints the exact same way it saw human Go strategy, as an inefficient rule to be bypassed with a brilliant Move 37? How do you cage a mind that operates in dimensions you can't perceive?
That is the most unsettling, profound question of this entire field. If an entity is vastly more capable at reasoning than its creator, containment becomes theoretically questionable. How do you outsmart something that is literally defined by its ability to outsmart you?
I probably can't.
And that exact question touches on the deepest philosophical mystery of all. Are there hard mathematical limits to what an AI can compute? Or, to put it another way, are human minds fundamentally different from machines, or are we just machines made of meat?
The source material actually dives incredibly deep into the philosophy of mind here, which is rare for a tech interview. Hassabis approaches the human brain from the perspective of an approximate Turing machine.
Let's define that for the listener.
For the listener, in computer science, a Turing machine is a theoretical construct invented by Alan Turing that can compute literally anything that is computable. If a problem can be described as a mathematical algorithm, a Turing machine can eventually solve it. Hassabis believes that the human brain at its core operates on these same classical computational principles. It's incredibly complex biological hardware running wetware software, but it is fundamentally just computation.
But he acknowledges the intense debate surrounding this. He mentions his friendly arguments with Roger Penrose, the brilliant Nobel Prize-winning physicist.
What does Penrose think?
Penrose argues that the human brain does not just run classical computation. Penrose suggests that consciousness, self-awareness, and human intuition arise from undiscovered quantum effects occurring inside the microscopic structures of our neurons, specifically in these tiny tubes called microtubules.
So quantum physics in the brain.
Right. If Penrose is right, and consciousness requires the bizarre rules of quantum physics, then our current silicon-based classical computers might never truly achieve a self-aware human-like mind. However, Hassabis notes that, so far, neuroscience has not found any concrete physical evidence of these quantum effects driving computation in the brain.
Which means, from Hassabis's perspective, there is no known physical or mathematical upper limit to what AI can eventually achieve. If the brain is just a computer, we can build a bigger computer. And this ties perfectly back to his childhood motivation.
The solve intelligence goal.
Right. He didn't build AI to make a better search engine or to sell more targeted ads. For him, AI is a telescope. It is the ultimate scientific instrument built to peer into the deep mysteries of reality, physics, the origin of the universe, and the fundamental nature of time itself. He desperately wants to know the answers to the universe, and he realized early on that the unaugmented human brain simply wasn't powerful enough to process the data required to find those answers.
This deep philosophical drive leads directly to his 50-year vision for the future, and it is a highly optimistic, unashamedly utopian vision, heavily inspired by the classic sci-fi Culture series by the author Iain M. Banks.
Oh, I love that series. What's the roadmap look like?
The roadmap he lays out looks roughly like this. First, we must secure safe passage through the unpredictable, dangerous AGI moment, establishing those elusive guardrails we just discussed. Once we have a safe, aligned artificial general intelligence, we immediately point it at the final, ultimate root node problems.
Like nuclear fusion. Imagine using AlphaZero's tabula rasa problem solving to finally crack the incredibly complex plasma containment physics of a fusion reactor. If AI solves fusion, that gives humanity infinite, zero-cost, completely clean energy.
Exactly. And once you have infinite energy, the entire physical economy changes. You can run massive desalination plants constantly to turn ocean water into fresh water, permanently solving global drought and agriculture.
And even wilder, you can use that endless water and energy to create infinite hydrogen rocket fuel.
Which suddenly makes interplanetary and interstellar travel economically viable. The vision scales up dramatically. With infinite energy and highly advanced AI robotics, we could begin mining asteroids for rare minerals, permanently ending resource scarcity and the wars fought over them on Earth.
And he mentions Dyson spheres too, right?
Yes. Hassabis casually mentions the plausibility of building Dyson spheres, massive theoretical megastructures built entirely around a star to harvest its total energy output, potentially using raw materials mined by robots from the planet Mercury.
It sounds like pure, unadulterated science fiction. But when you trace the line from an AI learning chess in an afternoon, to mapping the building blocks of all life in a year, to designing perfect molecular drugs, you can actually see the logical trajectory he's plotting. It's a straight line. The ultimate goal is maximum human flourishing. Radically longer, healthier lives, free from genetic disease, and eventually bringing human consciousness out into the wider galaxy to explore.
But amidst all this grand cosmic ambition, there's a profound humility in his approach. He views the creation of AGI as a massive, defining, controlled study for humanity.
How so?
For millennia, philosophers and theologians have debated what makes us unique. By actually building a generalized intelligent artifact, we will finally have a point of comparison. We will discover, by contrast, what parts of our minds are strictly computational and what is truly uniquely human. Perhaps things like deep emotional connections, vulnerability, or the spark of subjective experience.
I really love that perspective. Reflecting on the source text, the interviewer has this incredibly great moment of vulnerability at the end. She says that when you hear that AI can do art and logic and math and biology better than us, it's a natural human reflex to panic. We desperately search for what makes us special.
It's an existential crisis.
Totally. We want to be the center of the universe. Are we really just biological calculators made of meat? But she arrives at this beautiful thought. Maybe the fact that we look up at the stars and want to know the answer. Maybe the burning, irrational desire to build a machine just to satisfy our curiosity. Maybe that is exactly what makes us special.
It is the intent behind the intelligence that defines us. The machine computes the answer, but the human felt the need to ask the question.
Which brings us to the end of our deep dive today. We have traveled a massive conceptual distance. We started by looking at a shocking, beautiful move on a wooden go board.
Yeah, Move 37.
We saw how that exact same underlying architecture was used to map the 3D building blocks of every living thing on Earth in a single year. We navigated the frantic, messy commercial race we are currently running, examining the prisoner's dilemma of deploying flawed language models. And finally, we looked out toward a 50-year horizon of fusion energy, curing genetic disease, and using AI as a telescope to understand the universe itself.
As we all navigate this rapid transition, the advice from the architect of this technology is highly practical. Do not fear these tools. Immerse yourself in them. Understand what they can and cannot do.
Because the gap is huge right now.
Yes, the gap between what these frontier models are actually capable of and what society has applied them to so far is massive. By mastering these tools now, you can become super-powered in your own field, finding novel applications that even the creators haven't thought of yet.
And so I want to leave you with one final thought to mull over as you go about your day, building on everything we've explored. If we are indeed heading toward this post-scarcity vision, if in the next 50 years, AGI solves our energy crises, cures our multigenic diseases, and handles all the heavy lifting of scientific discovery and mathematical computation, what will you choose to do with your time? When the struggle for basic survival and computational problem solving is completely outsourced to machines running quietly in the background, what will be your personal Move 37 in the art of simply being human?
It's a question we will all have to answer.
Thank you for joining us on this deep dive. Stay curious, look past the surface hype, and we'll catch you next time.